All right, get ready because today we are going deep, deep into the history of the universe.
Yeah, it's going to be a wild ride.
We've got some awesome Wikipedia excerpts and a science article as our guides for this deep dive.
And believe me, it gets pretty mind-blowing.
We're talking the Big Bang, the first stars, maybe even a glimpse of what the far future holds.
Right, and you know what's really cool?
What's that?
Those first stars, they might have been total giants, like nothing we see today.
Okay, I'm hooked already. Let's do this.
It really is incredible how much we've learned about the universe's past. We're talking about events that happened billions of years ago,
Right.
but we can actually pinpoint when they happened, like with amazing accuracy.
That's amazing.
Yeah, but before we get ahead of ourselves, let's start with the basics, the Big Bang.
Okay, so when I hear Big Bang, I kind of picture this massive explosion that started it all.
Not exactly. It wasn't an explosion in space. It was more like the expansion of space itself.
Oh.
Think of it like a tiny, super dense point with all the energy and matter of the universe packed in.
Wow.
And then it just rapidly stretches outwards.
So not like an explosion, more like everything expanding.
Yeah, exactly. It's like blowing up a balloon, but instead of adding air, you're adding space.
Oh, I see. So the space itself is expanding. Got it.
Right.
But what about that very, very beginning? Have scientists figured that part out?
Well, not really. Our understanding kind of hits a wall when we try to look back to the very first moments.
Oh, so we don't really know.
Well, it's called the Planck epoch, and it's a bit of a mystery, like trying to read a book that's been burned.
So we're missing some pages from the beginning of the universe's story.
Exactly. The first few pages are gone. We can only guess at what they said.
Fascinating.
But we can pick up the story from where the book becomes readable. As the universe expanded and cooled, things started to change.
Like what?
Well, the fundamental forces, gravity, electromagnetism, the strong and weak nuclear forces, they all started to separate.
They were all together at first.
Yeah, it's like steam condensing into water, you know. At high
Yeah.
temperatures, it's all mixed. But as it cools, those distinct forms emerge.
Okay, I'm starting to get a clearer picture. So the universe is expanding, these forces are separating.
Right, it's like a cosmic dance getting started.
And what happens next in this cosmic dance?
Hold on tight, because this is where things get really wild. It's called the inflationary epoch.
Oh.
The universe expanded like crazy, exponentially, in a tiny fraction of a second. Imagine something a billionth the size of a proton, swelling to the size of a grapefruit, faster than you can blink.
Whoa, hold on, that's way too fast.
I know it's mind-boggling, but this super fast expansion helps explain why the universe looks so uniform on large scales.
So everything we can see today was once packed into something smaller than a proton.
Pretty much. Yeah, it's wild.
That is wild.
To put it into perspective, at the end of the electroweak epoch, the observable universe was only about 300 light seconds in radius.
So like the distance between the sun and Earth?
Less, even.
Wow, and I'm guessing things were still pretty chaotic at this point.
Oh yeah, it was a wild mix of energy and particles, like a cosmic soup, teeming with quarks and gluons.
Quarks and gluons.
Those are fundamental particles, and they were constantly colliding and interacting.
So like a giant particle party?
You could say that, and it's called the quark epoch, because it was so hot and dense that even protons and neutrons couldn't form yet.
Okay, so we've got this super hot, super dense quark soup.
Right.
How do we get from that to atoms and elements and everything we see around us?
Here's where it gets really interesting. As the universe kept cooling, those quarks started pairing up
Oh, to make?
to form hadrons, which include protons and neutrons. And there's this really cool twist here.
What's that?
Scientists think there was a little imbalance between matter and antimatter, like a cosmic game of musical chairs where one player is always left standing.
So there was more matter than antimatter.
Just a tiny bit. For every billion antimatter particles, there were 1,000,000,001 matter particles.
Wow.
And that tiny excess is why we have a universe made of matter today.
So everything we see, the stars, the planets, us, it all exists because there was this tiny bit more matter.
Exactly. All that matter and antimatter annihilated each other in a blaze of energy, but that tiny bit of extra matter, that's what formed everything we see.
It's mind-blowing that our very existence hinges on this 1 in a billion leftover particle.
It is. It's amazing.
So we've got these protons and neutrons now. I guess the next step is forming atoms, right?
Well, not quite yet. The universe is still a bit too hot for that.
Oh, right.
But something else was happening. Neutrino decoupling.
Neutrino what?
Decoupling. Imagine these tiny particles called neutrinos, almost massless,
Yeah.
suddenly stopping their interactions with other matter and just zipping off through the universe.
So like tiny cosmic travelers?
Yeah, kind of. They're still out there from the universe's earliest moments.
That's pretty cool.
It is. And while that was happening, the universe kept cooling, and then we have Big Bang nucleosynthesis.
Big Bang what now?
Nucleosynthesis, it's where the first light elements started to form, like deuterium, helium-3, helium-4. It's like the universe was getting its first chemistry set.
Oh, okay. So we're starting to get some basic elements cooking, but still no atoms.
Almost there. The next big event is recombination, about 370,000 years after the Big Bang.
Recombination. So things are coming together.
Exactly. The universe had chilled out enough for electrons to finally settle down and bond with those nuclei, forming the first neutral atoms.
So that's when atoms were finally formed.
Yep.
That's incredible. And what about all those photons that were bouncing around, creating a super bright fog?
Oh, they were finally free to travel unimpeded, making the universe transparent for the first time.
Ah, so this is where the cosmic microwave background comes from. It's like a baby picture of the universe, right?
You got it. Those photons, set free during recombination, they've been cruising through space ever since, giving us a snapshot of what the universe looked like almost 14 billion years ago.
That's amazing. So we can actually see back in time.
Yeah, in a way.
And even after all that, after recombination, the universe was still super dense.
Oh, yeah, about 1 billion times denser than it is today. Can you imagine?
That's incredible. We've come a long way from that chaotic quark soup. But before we move on, I wanted to ask about something you mentioned earlier. Helium hydride. What's the story with that?
Helium hydride, it might not sound very exciting, but it played a crucial role in setting the stage for the first stars.
Oh,
This simple molecule formed about 100,000 years after the Big Bang.
okay.
It later reacted with atomic hydrogen to create molecular hydrogen, and that was the fuel that would eventually power those first giant stars.
So it's like a stepping stone to the first star.
Exactly. It was a crucial ingredient.
Wow. So we've gone from this chaotic soup of particles to the first atoms and even a special molecule that helped kickstart star formation. It feels like we're about to enter a whole new chapter in the universe's story.
You're absolutely right. But before we jump ahead, take a moment to appreciate how far we've come. It's mind-blowing to think about the vastness of time and all the incredible transformations the universe went through to get to this point.
It really is. I'm ready for more. Let's see what the universe has in store for us next.
All right, let's dive into the next chapter.
Okay, so we've left behind the era of recombination. First atoms are forming. The cosmic microwave background is starting its journey through space. But now things get a little mysterious.
Yeah, we're entering the Dark Ages.
The Dark Ages, that does sound a bit ominous. So was the universe actually dark during that time?
Well, it's important to remember that even though we call it the Dark Ages, the universe wasn't completely dark. There were still photons from the CMB.
Right, that afterglow from the Big Bang.
Exactly, but that warm orange glow was quickly redshifting, becoming invisible to our eyes.
So no twinkling stars, just this faint, fading glow.
Pretty much. And with no stars or galaxies yet, the universe was definitely a much dimmer place.
It must have been a pretty quiet time then, right? No stars exploding, no galaxies colliding.
Definitely quieter compared to the early universe, but things were still brewing behind the scenes.
Oh, like what?
Well, even in this darkness, the universe wasn't completely silent. Neutral hydrogen atoms, for example, were emitting faint radio waves.
Radio waves from hydrogen.
Yeah, at a very specific frequency, it's called the 21-centimeter hydrogen line.
Interesting. So we could actually detect these signals from the Dark Ages?
In theory, yes. And on a much grander scale, something else was starting to make its presence known. Dark matter.
Dark matter, that invisible stuff that we can't see but know must be there.
Exactly. And it played a crucial role in shaping the universe we see today.
How so?
Well, because it doesn't interact with light, dark matter was free to clump together under the force of gravity,
Okay.
forming this vast, invisible scaffolding across the universe.
So dark matter was like the hidden architect of the universe.
That's a great way to put it. These dark matter structures, filaments, halos, and voids, they acted like giant gravitational wells,
Holy in!
pulling in the ordinary matter, mostly hydrogen gas, left over from the Big Bang.
So dark matter was setting the stage for the large-scale structures, the galaxies and clusters of galaxies.
Exactly. And within these pockets of denser hydrogen gas, pulled together by dark matter's gravity, the conditions were finally right for the formation of the very first stars.
The first stars, wow, what were they like?
We call them population 3 stars, and they were quite different from the stars we see today.
How so?
Imagine stars hundreds of times more massive than our sun, composed almost entirely of hydrogen and helium.
Wow, that's huge.
I know, right? And they burned incredibly brightly, but their lifespan was relatively short.
So they lived fast and died young.
Exactly. They burned through their fuel very quickly and ended their lives in spectacular supernova explosions.
Supernovae, those are like the grand finales of stars, right?
You could say that, and here's the crucial part. Those supernovae were the cosmic alchemists, forging heavier elements like carbon, oxygen, and iron, and scattering them throughout the universe.
So the death of these first stars actually paved the way for the birth of new stars, enriched with the building blocks for planets and eventually life.
Exactly. It's a remarkable story of cosmic recycling, the iron in our blood, the carbon in our bodies. It all came from those early supernovae.
That's amazing. So as these early stars and galaxies were forming, they were also changing the universe around them.
They were. Their intense radiation began to ionize the neutral hydrogen that filled the universe. This period is called reionization.
Reionization. So the universe was literally coming back to light.
That's one way to put it. It was a gradual process taking hundreds of millions of years.
And during this time, galaxies continued to form and evolve.
Yeah, they were merging and clustering together, drawn by gravity.
It's fascinating to think about these early galaxies, like baby versions of the ones we see today. Have we actually been able to observe any of them?
We have. Thanks to powerful telescopes like Hubble, we can peer back in time and see some of these ancient galaxies.
Wow, that's incredible. And what about those heavier elements created in the first supernovae?
Well, as new generations of stars formed from the enriched gas clouds, they incorporated those heavier elements, leading to more diverse stellar populations.
And with the universe becoming more transparent, those heavier elements could also form more complex molecules and eventually dust grains, the building blocks of planets. So we're seeing the seeds of future planetary systems being sown across the universe.
Exactly. And while gravity was still the main force shaping these larger-scale structures, a new player was about to enter the cosmic scene: dark energy.
Dark energy, the mysterious force that's accelerating the universe's expansion.
That's right, the universe had been expanding since the Big Bang, but gravity was trying to slow it down.
So it was like a cosmic tug of war?
Yeah, you could say that, but about 9.8 billion years after the Big Bang, dark energy started to win out, causing the expansion to speed up.
So that's when the universe's expansion started to accelerate.
Exactly, it marks the beginning of the dark energy-dominated era, which continues to this day.
It's fascinating how this invisible force, dark energy, has such a significant impact on the universe's evolution.
It really is, and this dominance has huge implications for the universe's future. It leads to various possible outcomes, from a gradual fading into darkness to a much more dramatic and violent end.
It sounds like we're about to explore the ultimate fate of the universe, which is both exciting and a little terrifying.
It is, but before we dive into those possibilities, let's take a moment to appreciate the incredible journey we've taken so far.
Yeah, we've traversed billions of years, witnessed the birth and death of stars, the emergence of galaxies, and the rise of dark energy.
It's amazing how much we've been able to piece together about the universe's grand story.
It really is. It's a testament to human curiosity and our drive to understand our cosmic origins.
Absolutely, and every discovery leads to new questions, pushing us to delve deeper into the mysteries of the cosmos.
And speaking of understanding our place, I think it's time we ventured into the realm of the future, the possibilities that await the universe, and us in the eons to come, ready for the final leg of our cosmic odyssey.
Absolutely. Lead the way. I'm eager to see what this deep dive reveals about the universe's future.
All right, so we've made it to the final frontier, the future of the universe. And after that incredible journey through billions of years, well, I gotta ask, what happens next? Is it all downhill from here?
Well, that depends on how you look at it. I mean, the universe as we know it has been around for what, like 13.8 billion years?
Yeah, something like that.
And it'll probably look pretty much the same for billions more, but, you know, on a really, really long time scale, things are going to change, that's for sure.
So what's in store for the universe long term? Any clues about its ultimate fate?
Well, we have some ideas, some pretty interesting possibilities, but let's start with where we are now, the Stelliferous era.
Okay, the Stelliferous era.
It started, about 150 million years after the Big Bang, and it's expected to last for, get this, trillions of years.
Trillions. With a T.
Yeah, it's the age of stars, new stars are still being born, galaxies are shining bright. But even the stars with the longest lifespans, they'll eventually burn out.
So even the stars eventually fade away. Does that mean the universe just becomes this, like, giant cosmic graveyard?
Not necessarily a graveyard, but definitely quieter, darker, for sure, as star formation winds down. The universe will slowly transition to an era dominated by stellar remnants, things like white dwarfs, neutron stars, and black holes.
Okay, and then what? What happens to all those remnants?
Well, this is where things get really interesting. The fate of the universe, it kind of hinges on a couple of things. The nature of dark energy and whether something called proton decay happens.
Proton decay, I've heard of that, but remind me.
Well, it's this hypothetical process where protons, those tiny particles that make up atoms, they spontaneously break down into lighter particles.
So they just, like, disintegrate.
Yeah, essentially. And if that happens, then even the matter that makes up stars and planets, it would eventually disappear too.
Wow, so the universe basically dissolves into this thin, cold soup of energy and particles. That's kind of a sad ending.
It is, but it's just one possibility. We're not even sure if proton decay actually happens.
Right, and what about dark energy?
Yeah, so we know dark energy is speeding up the expansion of the universe, but what we don't know is if it'll always stay the same or if it could change over time.
And if it changes?
Well, some theories suggest that dark energy might actually increase over time.
And what would that mean?
It could lead to a much more dramatic end to the universe, something called the Big Rip.
The Big Rip. Okay, that doesn't sound good.
It's not. In this scenario, the expansion gets so strong that it literally tears apart everything: galaxies, stars, planets, even atoms themselves.
Oh, wow. Okay, so it's not just things spreading out. It's like the universe is being ripped apart from the inside.
Exactly.
So is that the most extreme scenario, or are there even wilder possibilities out there?
Well, there's one more idea, but it's very speculative. It's called vacuum instability.
Vacuum instability.
It's the idea that the vacuum of space itself might not actually be stable.
Wait, so empty space isn't really empty.
It's more complicated than that, but the idea is that the vacuum could collapse into a lower energy state.
And what would that do?
It would trigger a kind of cosmic phase transition, changing the laws of physics as we know them. It's like hitting the reset button on the entire universe.
That's pretty mind-blowing.
It is. But remember, these are all just possibilities based on what we know now.
Right, because we still have a lot to learn about the universe.
We do. There's so much we don't know about dark energy, the nature of space and time, the fundamental laws that govern everything.
It's humbling to realize that even after this deep dive, we've only just scratched the surface of all the cosmic mysteries out there.
That's right.
But it's also really exciting to think about all the discoveries yet to be made, new insights that could completely change our understanding of the universe.
Absolutely. The quest to understand the universe, it's a journey without a final destination.
Yeah, each answer leads to more questions.
Ex-
So as we wrap up this deep dive, I'm left with a sense of awe at the sheer scale and grandeur of the universe, but also a deep sense of wonder about what the future holds. I think that's a pretty good takeaway for our listeners as well.
I couldn't agree more. It's been an extraordinary journey through cosmic time, and I hope it sparks some curiosity and wonder in everyone listening.
Yeah, who knows? Maybe one of our listeners will be the one to make the next big discovery about the universe. But until then, keep looking up and keep exploring.
That's the spirit.